Hello everybody and welcome back, not welcome back. This is my very first video on this channel, Orbital Velocity. And on this channel, I'm going to be talking about science, mostly rocket science though, because that's what I like and it's what I mostly study. You may know me as Commander Orange or Commander Orange Gaming or Plumpy Orange for those of you who are OG fans. You also may know me as Conrad, for those of you who actually know me in person. But yeah, this is my very first video on this channel. Well, my very first official video. But in this video, we're just going to be talking about the basic physics of rocket science. We're going to be talking about some of the history, a little bit how rockets work, just the basic physics of rocket science as the title says. So, we're going to be going over the Aelopile, hero of Alexandria. We're also going to be going to explore the first Chinese rockets, which were the very first actual things that you would call rockets. I'm also going to be explaining the physics of a rocket nozzle, Newton's third law, why oxidizer tanks are smaller than fuel tanks, fuel, max Q, aerodynamic pressure, and a bunch of the basic things about rocket science. So, let's get started. First, we're going to talk about a guy. His name was Hero of Alexandria, and this was way back in ancient Rome. And he made a device called the Aelopile, and what this was a little spherical chamber. Inside of it, there would be water, which would then be boiled off to make steam. And this little chamber would be able to spin around freely on a little axle. And basically, there's like a fire running under this chamber, and that would turn the water into steam, which would then go out two little nozzles on the outside of the chamber, and then one would be facing one direction, the other would be facing the other, and it would cause the entire chamber to spin around the axle, and it would gain speed and all of that stuff. This wasn't actually made for industry and stuff like that. It was actually mostly used to entertain the king and queen. It was just like an entertainment type thing because, whoa, it's spinning around very fast, so cool. But it wasn't used for any industrial purposes because of its very low torque, meaning that it can't spin large objects, so it's pretty much useless for anything too big until the steam engine would be invented, but that's later on. The Aelopile is actually the very first device that you'd actually call a rocket. It's not really a rocket, it doesn't move, but it's what we know to be the first device to use Newton's third law to its advantage. So next, we're going to talk about Chinese rockets. Now these were the very first actual rocket, and what it would be in a cartridge. Inside here there would be gunpowder, or some kind of flammable material. Usually it'd be gunpowder. And there'd be a fuse there, and it would light the gunpowder. And then, when the gunpowder is lighted, the back of the firework, well, the entire firework is enclosed except the back. So whenever the gunpowder is combusted, its only way out is to go out the back. There's no other way, because it's a completely enclosed cartridge. The only way for it to escape is out the back, and that's what it does. It shoots out the back and propels it forward. But the problem is that if you just have an open, gaping hole in the back of the firework, and all of the combustion, hot gas would fly out the back, it'd create barely any thrust. It wouldn't push it forward, barely anything. So what needed to be made is something called the rocket nozzle, which was a huge, a very, very good invention, very, very well made, very reliable, and is still used until this day. It's called the bell nozzle, and it makes sense because it's shaped like a bell. And what would happen is when the combusted gas comes out the back, it would actually be compressed through like a triangular tube. It'd be compressed, and then it'd come to a point where it's at its combusted gas comes out the back. It gets pushed into a small area, so it gains a lot of heat. And combusted gas, it never wants to be compressed. It always wants to expand. So it has to be compressed because there's no way out. But once it gets compressed, all of that heat comes to one point, and then it comes to the actual shape, which looks like a belt. It's like a bell shape. And then what it does is it begins expanding extremely quickly as it comes down the bell nozzle. It comes down very quickly. It begins gaining velocity extremely quickly because it pushes off the walls. And once it begins expanding, it actually goes supersonic and flies out the back extremely fast. And then that creates a much larger amount of thrust, which is why rocket engines actually have these kind of bell nozzles, because without them, rockets would be pretty much pointless. They'd go nowhere. But with the bell nozzles, it propels them forward much faster. So yeah, that is how a bell nozzle works. There are also rocket engines called aerospikes, which we'll talk about in some other video. But aerospikes are basically the same physics as bell nozzles, except a little bit different. We'll talk about that in another video, like I said. But bell nozzles are the most common, still being used to this day, but it was first made for Chinese rockets. These Chinese rockets were actually made for fireworks, but they're actually mostly used as weapons. These little fireworks would actually be connected to an arrow from a bow and arrow. And then whenever you'd release the arrow, a fuse would ignite, and it would ignite the firework. All of that hot gas will come shooting out the back, and it would actually propel the arrow forward much faster and with much more impact than a normal arrow would. So, pretty cool. Now, we're going to talk about fuels, rocket fuels. Now, gunpowder is pretty good, but in order to get to space, you need a lot more punch. So, what is made is liquid fuels, and these liquid fuels would be ignited in a combustion chamber in the rocket engine to be propelled out the back with much more power. So instead of gunpowder, they use some kind of fuel, which could be liquid hydrogen or liquid methane or liquid kerosene, some kind of fuel, and then it would have another tank with liquid oxygen, which is just like gas oxygen, like the stuff we breathe, but hypercooled to be a liquid. So there's liquid oxygen and the liquid whatever fuel you have, whether it's kerosene or liquid hydrogen or something. Then when it goes to combustion chamber, these two elements would react with some kind of spark, like an electric spark. So when these come together, the electric spark creates a very large amount of combustion, much more powerful than your average gunpowder. It would create a huge amount of combustion, which will then go out the rocket nozzle, use those same rocket nozzle physics, and then come out the back with way more force, much more thrust. There's another very, very good thing about liquid fuels, because if you just had gunpowder and went to space with that or some kind of solid fuel, then you wouldn't be able to turn off the engines in case of some kind of emergency. So if you light it, you can't stop. That sounds like a cigarette commercial, but once you light it, you can't stop it. With liquid fuel, that's a completely different thing, because you could just turn off the pumps, close the valves. The rocket engine will stop its combustion cycle, and it would just totally stop, it will stop its force. So that means that they're way more safe. They can do much more, meaning that they're very popular. There are also aerospikes, which are very rare. We'll talk about that in another video, of course. But, yeah, that's the bell nozzle and rocket fuels and why they're liquid. Now let's talk about why rocket fuels are hypercooled, because rocket fuels need to be cooled extremely cold. They need to be very cold so they can stay in their liquid state. So basically, whenever you have a gas and you hypercool it, hypercooling is just a fancy word for cooling it a very large amount. When you cool it down, then the molecules start to get closer and closer together, because they're losing energy in the atoms, and they're losing electromagnetic force in the from the atom. And atoms actually repel from each other with this electromagnetic force. If you have a low amount of electromagnetic force, they get closer and closer together. And as we all know from like first grade, no, less than that. Well, no, like first, second grade, the states of matter. You have solid, which the molecules are all very compacted together. Liquid, where they're all just floating around, all loose. And then you have gas, where they're just floating around. They're very widespread. And in order to create liquid, then you just need to hypercool that gas so the atoms and the molecules get closer together. And then, once it does that, it creates liquid fuel. Now you may ask, why do you even need liquid fuel? Well, the reason you need liquid fuel is if you have gas, just normal gas, inside of the tanks, then it's going to be very inefficient. Because the tanks would have to be like ocean size. You would have to have massive tanks because gas has a very low density. The molecules and atoms are very widespread, as I already said. They're very widespread, meaning that when they're combusted, they combust very quickly. So, in order to get to space, you need to have enormous tanks, meaning more weight, meaning more power, meaning bigger tanks, and then that just keeps going. It's like a big paradox. So instead what you could do is hypercool this gas, turn it into a liquid, and have a large amount of fuel all in one small area. So these tanks, the problem is the liquid always wants to expand back in its gas state because oxygen and hydrogen, they're just always naturally a gas. That's just their natural state. So instead what you could do is pressurize them. Keep them in their liquid state by pressurizing the tanks. We'll talk about this way more in another video. But the molecules want to get back to their original state, meaning that if there's no kind of depressurization and the tanks stay at their normal state, then the molecules are going to get further and further apart, and eventually the tanks will just explode, destroying the entire rocket. So instead, what you could do is slowly depressurize the tanks using little valves. It's just little bursts of pressure coming out of the tanks in order to keep pressure in the tanks so they don't explode. Another thing is a COPV, which is a composite overwrapped pressure vessel. And what that does is it's a very strong tank. It is fairly thin walls, but it is a very strong tank, and it keeps pressure. It keeps the fuel pressure at a steady rate just by strength. It basically just keeps it in a steady pressure just by basically squeezing it so it doesn't pop, so the fuel tanks don't just explode and destroy the entire rocket. COPVs are very, very hard to produce and very hard to actually make. So COPVs are pretty rare. There's rockets like the Electron rocket that Rocket Lab makes. They have COPVs, I think. Yeah, they have COPVs. But most rockets just have normal, slowly depressurizing tanks that just depressurize using small bursts that burst off the rocket. You may have seen those if you watch a rocket launch. You could see sometimes like little spurts of pressure just bursting off the rocket. That's perfectly normal. That's nothing to worry about. It's just the keeping the tanks from exploding. So next, let's talk about apogee, apoapsis, and perigee. This is where it gets a little bit harder. So now we're talking about orbits, which is basically like you're infinitely falling around some kind of celestial objects that's floating through space. Now, this object has to have a large amount of gravity for this to work, meaning things like planets, large meteors, moons, things like that. Because gravity is a very weak force, but if you have a large amount of mass, then you'll have gravity. Gravity is a very powerful force only when you have a large amount of mass. The more mass you have, the more gravity you have. That's just a thing. So, first of all, let's talk about perigee. If you have an orbit, it's never going to be perfect. It's never going to be a perfect circle. There's always going to be one point which is closer to the planet. Let's just take Earth, for example. There's going to be one point in the orbit closest to the Earth, and one point of the orbit further away from the Earth. And this is called the perigee. Let's just say here, you have an orbit, you have 2 points, and then you have a line in between. That would be the perigee. The most extreme points in the orbit, meaning the furthest point in the orbit and the closest point in the orbit. and that would create the perigee. Now after this is the apogee and apoapsis. So you have the apogee, which is the apogee, which is the closest point to Earth, is the closest point to the planet. That's the apogee. And the apoapsis, which is the farthest point. And then both of these, the apogee and apoapsis, this creates the perigee, which is the two most extreme points in the orbit. Now, G is just basically a word stem for Earth. So if you have, let's just say you're orbiting the sun or something, then that would be an apohelion, or an, it'd be helion instead of G, basically. So there'd be perihelion, apohelion. But anyway, now we have orbits and how to get into orbit. This is probably the most challenging part of getting a rocket into space. In order to get into orbit, you have to be moving extremely fast. Basically what an orbit is you're basically infinitely falling around a celestial object. So let's just say you just launched straight up from a planet. You just launched straight up. You would never get into orbit, and I'll talk about why in a second. But if you just go straight up, you're obviously going to get to space eventually, but it's going to have a huge impact on fuel. It's going to be extremely inefficient, and you're going to need a ridiculous amount of fuel inside of the tanks. The rocket will need to be absolutely gigantic for that to even work. So instead, there's something called an orbit, and what that does is, let's just say, first of all, you have a soccer ball. If you throw it perfectly up, it's going to come straight back down in a straight line, right back on top of you. But if you throw it diagonally, it's going to create an arc. And that arc, the very top of the arc, is going to be the apogee. And the apogee is the furthest point from Earth. So it's not just in orbits. An apogee could be like the highest point in an arc from a soccer ball. So you throw a soccer ball, its highest point, when it reaches its highest point, that's obviously going to be the furthest point from the from Earth, and that will be the apogee. So if you have a rocket and you launch in something called a gravitational turn, you go straight up, and then you do something called a curve, which a lot of you may have realized during a launch. A rocket actually curves in order to get into orbit, and when a rocket curves, its path back down to Earth is now going to be an arc. So where the rocket is right now is the apogee. And as it keeps going up higher and higher, its apogee is going to extend, and therefore the entire arc is going to extend. And since the Earth is round, what happens when the arc keeps extending, the rocket keeps going up and keeps going further and extending the apogee. And what it does is that the arc from the rocket, the gravitational arc, is actually going to wrap around the planet. And eventually, the end of the arc, when that point when it hits the ground, is actually going to come in line with the apogee. And you keep going up. The entire arc goes all the way around the planet, and then it comes straight back. So now what happens is you're falling, oh no, I'm falling back to a planet, and then you're just going to swing straight back around and loop around. And you go into something called an orbit, where you're infinitely looping around the planet. Well, it's not really infinite if you're in LEO, which is low Earth orbit. If you're in low Earth orbit, then it's not infinite. Eventually, if you're in low Earth orbit, there's still molecules. It's not like complete dead space. It's not like interstellar space. There is still molecules, and that's going to create some friction, and that will slowly slow down your spacecraft. And then as it slows down, it will start dipping back down into the atmosphere. And then what that's going to do is it's going to slowly contract the orbit until you're no longer in orbit. Then you'll crash. This is called a parking orbit. The only time when it's in use is like the space shuttle on like super short missions where they go back, repair a satellite, go to the ISS or something, and then go straight back down. Or like the new Dragon capsule from SpaceX, they go into low Earth orbit for only a little while just to go to the ISS. And yeah, there you go. That is the apogee, apoapsis, and perigee. Now, let's talk about orbital velocity. Orbital velocity is actually a pretty complex type of thing when it comes to physics, so we'll talk about this more in a video where we'll dive deeper into orbits. But just to cut it short, orbital velocity is the speed you need to go to orbit. It's at least orbital velocity, and orbital velocity is 17,500 miles an hour. If you go any slower than that, you can't go to orbit. You just can't go to orbit. It's physically impossible, which is why planes can't fly into orbit, which is why rockets are literally the only option in order to get to orbit. Rockets are the only option because they're the only devices that mankind has ever made that could reach such crazy speeds. If you can't picture 17,500 miles an hour, which is crazy fast, think of this: 17,500 miles an hour is about Mach 30. Which Mach 30 is 30 times the speed of sound. You need to be moving that fast to get into orbit. It's that or faster, or else you can't go to orbit. You can go to the edge of space, but you can't go to orbit. You have the Concorde, which was the fastest passenger plane, which was a 2.5 Mach or something like that, 2.5 times the speed of sound. So just imagine that about 15 times more. It's crazy that rockets can get to such incredible speeds that fast. So now let's talk about max Q and aerodynamic pressure. This is a fun one because aerodynamic pressure is one of the biggest challenges when putting a rocket into space. Because if you have a rocket moving at a Mach 30, 30 times the speed of sound, moving at orbital velocity, you're going to come across a huge amount of aerodynamic pressure. Which, aerodynamic pressure is basically the amount of pressure or stress on the rocket when it is moving upwards. So when the rocket is moving upwards, air molecules crash into the top of the rocket as it's moving to go into orbit. And that creates aerodynamic pressure, which is the amount of pressure pushing down on a rocket. Aero, which is just Latin for air. Dynamic, which means movement, and then pressure, because it's pressure pushing down on the rocket. So as the rocket's moving up, it has a huge amount of aerodynamic pressure, which is air molecules pushing down on the rocket. And gravity is just an easy part of the equation. To get into orbit, if there's no aerodynamic pressure on this planet, it'd be easy to get into orbit. You could get into orbit no problem, which is why getting off the moon in the Apollo missions to get off the moon was so easy, because the moon has no air, a very small amount of molecules, and has no atmosphere, so it's easy to get into lunar orbit, to get off a lunar surface and to get into lunar orbit because you have no aerodynamic pressure. So aerodynamic pressure, now you know what that is, but max Q, that stands for maximum quotient. And to cut that short, max Q is the maximum amount of aerodynamic pressure the rocket experiences on its way up. So a rocket accelerates extremely quickly as it's on its journey to go into orbit, and max Q is the point where it has the most amount of aerodynamic pressure, has a huge amount of force on the tip of the rocket, which is a huge challenge because rockets need to be made extremely well, extremely structurally, they have to be very strong, very well made, so they don't just collapse like a tin can under the aerodynamic pressure of the Earth's atmosphere. So now let's go into stabilizer fins and stability. Now stabilizer fins are always a triangle. And the reason for that is, well, I'm going to say that in a second, but they're triangles, meaning that the lower part of the stabilizer fin has way more area for air to hit. Because if air is hitting into a stabilizer fin, then most of the air is going to be hitting the lower part of the fin. Because obviously, since it has a much larger area than the tip of the triangle, the bottom of the base of the triangle is always going to be way more molecules are going to be hitting that, because there's just a larger amount of area for it to hit. So stabilizer fins, there's 4 of them all around the rocket. There could sometimes be more. As 4 stabilizer fins, one on each side of the cylinder, which is a rocket needs to be a cylinder, which we'll talk more about why most rockets need to be cylinders in order to actually get into orbit. We'll talk about that in another time. But these stabilizer fins, which are on the rocket, whenever the rocket, if you have a rocket moving upwards, if it tips this way, if you don't have stability, then it's just going to keep tipping. Because the problem with cylindrical rockets is if it's moving to an airflow, which is moving down like this, the cylinder will always want to be perpendicular to the airflow, meaning that if you have a rocket, it's always going to want to tip this way if it doesn't have stability. It's going to want to tip this way, and that would just be terrible. The rocket would crash. So, in order to keep it stable, you have these stabilizer fins, and whenever the rocket tips this way, then air comes down and hits a stabilizer fin, which is, we'll just say right here. The air hits the bottom part of the stabilizer fin and pushes the whole rocket this way. This is why all rockets, whenever you have stability fins, they're always at the base. Because whenever you have a stability fin, the air comes down and hits the bottom of the stability fin and then pushes it up back into its stable upwards position. So these stabilizer fins are on all four sides, so you have an equal amount of stability on all of the sides. Now if you have if your stability fins are too small, then what's going to happen is the rocket's going to flip over because it's not going to have enough area for it to hit in order to keep it stable. So, another problem is the nose cone of a rocket. A nose cone of a rocket all rockets need to have a nose cone. If it doesn't, it's just going to get crushed by the aerodynamic pressure. If you have a nose cone, the problem is if you don't have one, the rocket is going to be crushed. Because if you have a flat surface, when the airflow comes in, it's going to slam straight into that flat area on the top of the cylinder. And it's going to crush the whole thing. But if you have a nose cone, the air comes down and it separates at the tip. It separates down, it separates at the tip, and this reduces aerodynamic pressure by a huge amount. So all rockets need to have a nose cone, or else it's just not going to work. It's going to be crushed. It's going to be destroyed. So, the problem with the nose cone is for stability. If your rocket is tipping this way, the air is also going to hit the nose cone. Meaning, since the nose cone is a tipped surface, it's going to hit the nose cone a very, very large amount. It's going to hit it and it's going to try to push it over. So the stability fins need to be fairly large, usually like about a fourth or a third of the rocket. Because if they're not big enough, the nose cone, the force from the air hitting the nose cone is just going to tip the rocket right over and destroy it. So the stability fins need to be fairly sizable in order to keep the rocket stable. Now you may have realized that actually some rockets don't have stability fins, and this is because they either have something like grid fins or RCS, which is reaction control system. Now we'll talk about this way deeper in another video. But, depending on the rocket's needs, sometimes it doesn't have stability fins. We're going to talk about control besides stabilizer fins way deeply in another video. But depending on your rocket's needs, sometimes you don't need stabilizer fins, sometimes you do. Now, after this is the final thing we're going to discuss today, and that is why rockets almost always launch from the equator or near the equator. So you may have realized that most rockets actually launch from near, very close to the equator. Most rockets launch from Cape Canaveral, Florida, which is where Kennedy Space Center is, and that's where almost literally every single U.S. rocket, well, not every single, but 90% of U.S. rockets have launched from Cape Canaveral, Florida. SpaceX rockets, NASA rockets, tons of other rockets. They all launch from Cape Canaveral, U.S. rockets. Some of them launch from Texas, like South Texas, which is also near the equator. But either way, pretty much all rockets launch from the equator, unless it's a Russian rocket or something which means that they have a huge disadvantage. Chinese rockets, Russian rockets, since they're way up north, they have a huge disadvantage. And the reason for that is, picture a circle. Whenever it's spinning around, let's have a point in the center of the circle that's spinning around, and then also a point on the outside of the circle. And basically, whenever the inner part of the circle spins around, it's going to be moving very slow, since it has pretty much no distance to move completely around. So as it's moving, it doesn't have to move very fast, because in order to move the entire distance around the circle, it doesn't need very much speed. But if you're on the outside of the circle, you have a much larger distance going all the way around the circle. So the entire circle is spinning at the same speed, pretty much, but the outside of the circle needs to move way faster than on the inside, because it has a much larger distance to travel. So now think of this on a 3D globe, a sphere like our planet. If you're near the equator, you're going to be moving much faster, because you're going to have a much larger distance to travel, since the equator has like a bulge, and then the tip of the planet is way, narrower, because that's just how spheres work. So to cut this short, the closer you are to the widest point of the circle, the faster you're going to be moving. So what this does for rockets is, if you're at the equator, you're going to be moving much, much faster than if you're up north. And since you're moving much faster, whenever you launch, you get an extra boost into orbit, meaning your rocket doesn't need to do as much work to actually get into orbit. Which is why pretty much all rockets are near the equator, except Russian rockets, Chinese rockets, stuff like that. They have a very large disadvantage, since they're way more up north. Meaning that if you're launching from, like, let's say Moscow, Russia, you launch from there, you're not going to have a very large boost into orbit. You're barely even going to get a boost. So yeah. U.S. rockets are lucky, because they get an extra boost into orbit, meaning it's not as hard to get into orbit, and it's not as intense of a process. It's still very hard to get into orbit, but the nearer you are to the equator, the easier it is to get into orbit. Those are all of the basic things you need to learn about rocket science. It is the jumpstart you need in order to study rocket science, and it is the stuff you need to actually begin to understand it. So I hope you guys like this video. Make sure to like and subscribe like usual, because it really helps the channel out. So yeah, I hope you guys learned something. Have a great day, and yeah, goodbye.